Today we are going to discuss a most important phenomenon in superconductivity, and this is actually regarding a very important uh, phenomenon which is called Josephson effect. Actually, this Josephson effect is of two types. First one is known as DC Josephson effect and another is called AC Josephson effect. Actually, in this first lecture on this Josephson effect, I would like to discuss only the DC Josephson effect, and in a subsequent second lecture we will see the concept of AC Josephson effect. But before knowing the idea or concept of this Josephson effect, I would like to introduce you a single particle tunneling. I hope you have definitely studied the process of tunneling, or you can say barrier penetration, in your course on quantum mechanics. You know, when an electron is incident on a potential barrier whose height is greater than the energy of the electron, even then quantum mechanically there is a finite probability that electron tunnels or electron transmits through the barrier, and this phenomenon is called tunneling or the barrier penetration. Actually, that idea has been used in this particular phenomenon which we are going to discuss. But before knowing about the Josephson effect, as I have told you that first of all I would like to introduce you the single particle tunneling. Although I have not written those facts here, but just as an introduction I am introducing it. In this figure you can see I have considered there is a superconductor marked by 1 in this figure, you can say, and marked by 2. And these two superconductors have been separated by a very thin insulating oxide layer, which I have shown by this dotted region. But before this, let us consider that this 1 and 2 are not superconductors, but these are metals, or you can say the normal conductors. So first of all I am considering that 1 is a normal metal or normal conductor, not a superconductor, and 2 is also a normal metal or normal conductor. Okay, and that is separated by this thin insulating oxide layer. Actually, the thickness of this layer is very small. This is almost 10 angstrom to 20 angstrom. Okay, I have not shown this normal metal contact in this figure, but you can understand. Okay, so we consider that two metals separated by an insulator, as you can see in this figure. Instead of superconductor we have considered normal metals. Actually, the insulator normally acts like as a barrier to the flow of conduction electrons from one metal to the other. Okay, and if the barrier is sufficiently thin, as I have told you that its thickness is almost 10 angstrom to 20 angstrom, then there is a significant probability that an electron which impinges on the barrier will pass from one metal to the other. It means electron which is incident or which is in the region 1, that will pass through this barrier in region 2, and there will be a finite probability of this event. Okay, actually this is known as barrier penetration or tunneling. Okay, actually in many experiments the insulating layer is simply of thin oxide layer formed on one of two evaporated metal films. Okay. So when both metals are normal conductors, the current voltage relation of the sandwich or tunneling junction is ohmic at low voltages. When you say that the electron flows from one region to another through this insulating oxide layer, the flow of current will constitute a current, and that current is actually ohmic. When you say that current is ohmic, what does it mean? You know, according to Ohm's law, V is equal to IR, or you can say that I is equal to V over R. Okay. So in this condition, actually I is directly proportional to V. This is called Ohm's law. And if I increases with increase in V, that is increase in potential linearly, in fact in that condition the resistance is called ohmic. Okay. And so it is found that when both metals are normal conductors, okay, the current voltage relation of the sandwich or tunneling junction is ohmic at low voltages, with the current directly proportional to the applied field. It means when you will plot the electric current in this condition in against of the voltage, you will get this straight line. Okay. But all these things you will see when this insulating oxide layer separates the two normal metals, which I have not shown in this figure. In this figure I have shown superconductors, but mentally you can think that at the place of superconductors there are normal metals, then this type of phenomenon takes place. Okay. Now after that, scientists have tried to what will happen when actually one of the metals will be replaced by a superconductor. So now let us consider that one is the normal metal, but this 2 is not a normal metal, but let us say that this is actually a superconductor. Okay, then what will happen? So 1 is normal metal and 2 is superconductor. Okay, then what will happen? Superconductor. This has been also not shown in this figure. Okay, actually it is found that if one of the metals becomes superconducting, the current voltage characteristic changes from a straight line to a curved line. As you can see in this condition, you can say that the resistance does not remain ohmic and the Ohm's law is not followed. This will actually happen when this junction is separated by a normal metal to a superconductor. Okay, so when in this condition you will plot I against V, then it is found that the current variation in against of voltage or current voltage characteristic does not remain a straight line, but it varies like this. This is almost like this, the non-linear variation. Okay, and after that Josephson performed experiment by replacing this normal metal to a superconductor. Okay, it means now we are talking about the situation when this insulating oxide layer is separates actually two superconductors. Then one is also a superconductor. You can see one is now a superconductor and 2 is also a superconductor. Then what will happen? Then what will happen? That is the subject matter of Josephson effect. This is also a superconductor. Superconductor. then what will happen? Okay. Actually, whenever you talk about a superconductor, you know, in the superconductor, instead of electron, we talk about the correlated pair of electron, which is called Cooper pair. So actually, in this condition, the two when the two pieces of superconducting material will be separated by a thin insulating oxide layer, whose thickness I have shown in this figure by 2a. Okay. Then the Cooper pairs can tunnel through the insulator, giving a current from one superconductor to other. Okay. And this characteristic curve, which has been shown here, now will be not found. Okay. Because that was the case when the one a specimen was of superconducting nature and another was metal. Then you have non-linear current voltage characteristic. When both are metals, then you have linear voltage current characteristic. But now we are going to see what happens when both of these 1 and 2 are of superconducting nature. Okay. Actually, as I have told you, in previous two cases, electron was moving from one region to another. But in this case, the Cooper pair will move from one region to another, passing or tunneling through the insulating layer. Actually, this phenomenon was first of all observed by B.D. Josephson, and he predicted that supercurrent consisting of the correlated pair of electrons, which are also called Cooper pairs, can made to flow across an insulating gap between two superconductors, provided the gap is enough thin. Okay, gap is very small, almost of the order of 10 angstrom to 20 angstrom, or you can say 1 nm to 2 nm. Okay, actually such a junction is called weak link, or you can also call it Josephson junction. This is called Josephson junction. So this is and what is the different fact in this case? Now let us see. Actually, the layer of insulator acts as a potential barrier, okay, for the Cooper pairs, and a fraction of current approaching this barrier from left to right, you can see, from left to right, manages to tunnel through the barrier and continue on the other side without any loss of net energy. Okay, so the junction permits the flow of current without any net loss of energy, even when the potential difference across it is zero. So when no potential difference is applied, no voltage is applied across this junction, even then a direct current flows from one region to another. This is the remarkable fact. When these two, 1 and 2, were actually of metallic specimen or conducting nature, then current flows. But after the application of voltage, you have seen the current voltage characteristic curve. And also in the case when 1 is of superconducting nature and 2 is a normal metal, or vice versa, even then the current varies with voltage. It means we get current, the tunneling effect takes place when voltage is applied across the junction. But when these two materials 1 and 2 are of superconducting nature, then a direct current flows from one region to another without applying the voltage. It means we apply no voltage, zero voltage, V equal to 0, but I is not equal to 0. Actually, this phenomenon is known as DC Josephson effect. Okay. So you can say that a DC current flows across the junction in the absence of the any voltage or in absence of any electric or magnetic field, and this phenomenon is called DC Josephson effect. Okay. So I think you have clearly understand what is this DC Josephson effect and when it takes place, and what is the remarkable difference when 1 and 2 were metals, when 1 were superconductor, 2 were metals, and in this case we find that there will be no voltage across the junction, but we will get current. So how without applying any voltage across the junction, electric current is constituted by the Cooper pair, that will be explained by a proper theory. So what is this DC Josephson effect? You have understand in a qualitative manner this phenomenon. Now by a proper mathematical calculation, by a proper theory, we are going to see the explanation of this DC Josephson effect. Actually, in the next lecture we will see about the AC Josephson effect, and in that case you will see when a voltage will be applied across this junction, then it is seen that an AC current flows. In absence of voltage, DC current flows, but in a presence of voltage across this barrier or across this insulating oxide layer, AC current will flow. And that phenomenon is actually called AC Josephson effect. But that is the subject matter of our next lecture. Okay. So now we are going to see the proper theory of this DC Josephson effect first in this lecture. Okay. And all those facts regarding this Josephson effect, not for the single electron tunneling, I have mentioned it here for your convenience, because the question will be asked for Josephson effect. So I have not mentioned those facts for the metallic contact, for the one superconductor and another metallic contact. I have not mentioned those. But what is this DC Josephson effect? What happens in this case? I have written here for your convenience, and you can note down these facts in your notebook, and that will be a good answer for this question in your examination. So I am just now again giving a reading of this so that everything will be clear to you. You can see in a Josephson junction, two pieces of superconducting material are separated by a thin insulating oxide layer of thickness 2A. I have marked it 2A, but the value of 2A is from 10 angstrom to 20 angstrom. Okay. The Cooper pairs can tunnel, or you can say the correlated electron pair can tunnel through the insulator, giving a current from one superconductor to another. B.D. Josephson predicted that a supercurrent consisting of correlated pairs of electrons, that is Cooper pairs, can made to flow across an insulating gap between two superconductors, provided the gap is small enough. Such a junction is called weak link. This is called weak link, or it is also called Josephson junction. Okay. The layer of the insulator acts as a potential barrier for the Cooper pairs, and a fraction of the current approaching this barrier from left or right manages to tunnel through the barrier and continue on the other side without any net loss of energy. Okay. Thus, the junction permits the flow of DC current without any loss of energy, even when no voltage is applied. Mark it, no voltage is applied. Even then we get the DC current flowing from one region to another through the potential barrier, okay, across the, and this phenomenon is called DC Josephson effect, okay. So you can say that DC Josephson effect is the flow of DC current across the junction in the absence of any electric or magnetic field. Actually, when voltage is applied across the junction, then you know electric field is produced. But when voltage will be not applied, there will be no electric field, even there will be no magnetic field. But in absence of electric and magnetic field, current flows, direct current flows. And you will see by the proper theory later on that this current will vary in accordance with the phase difference, okay. And so we have a current without applying any external voltage, and this phenomenon is called DC Josephson effect, okay. So I think now what is this DC Josephson effect has been definitely very clear to you. Now let us see the quantum mechanical approach or quantum mechanical theory to explain this DC Josephson effect. And for this, let us consider that this psi1 is the probability amplitude, or you can say wave function, of the Cooper pair on one side. This is the wave function or the probability amplitude of the Cooper pair in left side, let us say in region 1. And this psi2 is the probability amplitude or the wave function, you can say, for the Cooper pair on the other side. We consider it, okay. And for the simplicity of calculation, we consider that both of the superconductors, that is the superconductor which I have marked by this 1 and 2, for simplicity we consider that both of these superconductors are identical, okay, and both have been kept at zero potential, okay. Both are at zero potential, so there will be no potential difference across the junction, okay. Now applying the time dependent Schrodinger equation, we can find the supercurrent density, and how we can find it now you can see. You know, the time dependent Schrodinger equation is given as IH bar del psi by del t equal to H psi. This is actually the time dependent Schrodinger equation, okay. So when you will apply this time dependent Schrodinger equation for the Cooper pair in left side, that is in region 1, and in right side, then what will be the time dependent Schrodinger equation you can see. This is IH bar del psi1 by del t. This is for the region 1, and that will be equal to H psi1. H is the Hamiltonian, you know. But this H psi1 has been written as H bar T psi2. How we can write this H psi1 equal to H bar T psi2? What is this T? Why psi1 has been replaced by psi2? I will clear it. First of all, see this equation, okay. And for the Cooper pair in the right side, that is in side 2, the Schrodinger equation will be IH bar del psi2 by del t equal to H psi2. Hamiltonian is same because we have considered that both the superconductors are identical. And that is written as H bar T psi1. Actually, what is this H bar T? In fact, you know, this H bar T is the effect of electron pair coupling or transfer interaction across the insulator. Actually, this is, you can say that this is just a transformation matrix. This transforms this psi1 into psi2, psi1 into psi2. This phenomenon is just like a phenomenon taking place in case of transformer. when in there will be a reflected resistance which reflects the resistance of primary into the secondary. Just like that, this H bar T actually represents the effect of electron pair coupling or transfer interaction across the insulator. Actually, this T has a dimension of frequency, and you know H bar has a dimension of energy into time, that is joule second. So this will be joule second, and frequency has unit second inverse. So this will be H bar T has dimension of only joule, which is of energy, which is the dimension of H. Okay. So T has the dimension of frequency, or you can also say that T has the dimension of rate. Okay. In fact, T is a measure of the leakage of psi1. Mark it. T is the measure of leakage of psi1 into the region 2. It means how much psi1 has been leaked into the region 2, that is actually measured by T. And so applying T, this psi1 is changed into psi2. Okay. And similarly, this and psi2 into the region 1. Okay. Actually, you have seen, we have considered that, or Josephson has considered that the insulator between the two superconductors was very thin. Only then this phenomenon takes place. But if you will consider that the insulator between the two superconductors is very thick, not thin but very thick, in that condition there will be no pair tunneling. Cooper pair will not tunnel from one region to another, and this T will be equal to 0. And so this Josephson effect will not take place. Okay, there will be no supercurrent flowing from one region to another without applying any voltage. Okay, and this will happen when you consider that the insulating junction is very thick. Okay, so Josephson effect, this is a necessary condition for this phenomenon, that the insulating layer should be very thin, because in case of thick insulating layer, this T will be actually almost 0, and so there will be no tunneling of this Cooper pair from one region to another. Okay, and you also see same thing in case of the quantum mechanical tunneling. When you study barrier penetration, then actually inside the barrier the amplitude decreases exponentially, and if the barrier has a large thickness, then the amplitude will become 0 and there will be no transmission of barrier. So for the transmission of barrier, the thickness should be small. Okay, so that the probability of transmission does not fall to 0 inside the barrier. Okay, now let us see. You know that this psi star times psi, this is the measure of probability density, or you can say here that this is the measure of pair concentration. Okay, so if N is the concentration of a Cooper pair, then this N is defined as psi star times psi, which is the measure of probability density, or it is equal to mod of psi square, and this is actually constant here. Okay, in fact, at absolute 0 temperature, this N is half of the concentration of electrons in conduction band. Why? Why this will be just half of the concentration of electrons conduction band? Because you know N represents the concentration of a pair. It means two electrons has been combined and now they have only one identity. So since N refers the pairs, that's why N will be just one half of the concentration of electron in the conduction band. Okay, and so that you can write psi equal to n to the power half times exponential to the power I means iota, theta of r. Actually here theta, this represents the phase factor, okay? And so its complex conjugate, that is psi star, this will be given by n to the power half e to the power minus iota theta of r. And so from here you can see, if you take the product of this psi star and psi, then this exponential factor, the product of these two exponential factor will be 1, and n half times n half will become n. So in this way you can express this psi. Now using this idea, we will define psi 1 and psi 2. That is the probability amplitude of the Cooper pair in left side and in right side, we will define on this line. Okay. So now let us see. Psi 1 you can define as, this is n1 to the power half times exponential of iota theta 1, and psi 2 equal to n2 to the power half times exponential iota theta 2. Okay. Now as in this equation 1, you can see in Schrodinger time dependent equation, we have the factor del psi 1 by del t and del psi 2 by del t. So now first of all we will evaluate the value of del psi 1 del t and del psi 2 del t, simply differentiating these psi 1 and psi 2 partially with respect to t. Okay. So you can see now we will, first of all we are going to find the value of del psi 1 by del t. See here the expression for psi 1. This is just a product of two functions. First one is n1 to the power half and another is exponential of iota theta 1. So using the product rule for differentiation, you can see when you will differentiate this n1 to the power half with respect to t, then you have to keep this e to the power I theta 1 at each. So this will be 1 over 2 n1 to the power minus half times del n1 by del t, and this factor is at each, you can see, plus. Now we will keep this n1 to the power half at each, and we will differentiate this e to the power I theta 1 with respect to t. Okay. So this will be I times e to the power I theta 1 times del theta 1 by del t. Okay. Now let us see. This RHS can be simplified to some extent. You can see that this del psi 1 by del t, this will be half n1 to the power minus half times e to the power I theta 1 times del n1 by del t, plus. Now see here, this n1 to the power half times e to the power I theta 1. What is this? This is simply psi 1. So instead of this factor, I have written here psi 1, you can see. But from this equation 1, you can also find the value of this del psi 1 by del t. You can see this is I h bar del psi 1 by del t equal to h bar t psi 2. Okay. So from here you can see that this del psi 1 by del t, this will be t over I times psi 2, and 1 over I is minus I, so this is minus I t psi 2. Okay. So if you will substitute this value of del psi 1 by del t in this equation, then you can see we have the result del psi 1 by del t is equal to this much. I have just written the expression, and that will be equal to minus it times psi 2. Okay. Now in the similar manner, when you will differentiate this psi 2 with respect to t partially, and again you will find del psi 2 by del t from this equation 1, then a similar result you will obtain. And for getting this result, you can follow a trick. when actually the subscript 1 will be replaced by 2 and 2 will be replaced by 1, you will get the result. So here there is 1, so you can now write del psi 2 by del t, and that is equal to 1 over 2. Instead of n1, now we have to write n2. Okay. Instead of theta 1, you have to write theta 2. Instead of n1, again you write here n2. Okay. Here is psi 1, so you have to write psi 2, and for theta 1, you have to write theta 2. Okay. And in RHS, instead of psi 2, you have to write psi 1. Okay. So in this way, we obtain the value of del psi 1 by del t and del psi 2 by del t. Okay. Now let us see. Remember this a very important algebra to get the proper result. Actually, our aim is to find the rate of change of this concentration with time, which actually constitute current. You know, when charge carrier flows, current is constituted. So what is the rate of flow of charge carrier? That is, what is the value of del n1 by del t and del n2 by del t? That will decide the current. And for getting the values of del n1 by del t and del n2 by del t, we have to follow a simple algebra. And what is that algebra? Actually, we have to multiply this equation number 2. Mark this equation 2 by the factor n1 to the power half times e to the power minus I theta 1. Okay. And we also use a relation theta 2 minus theta 1 equal to delta. That is, when in our calculation there will be a factor theta 2 minus theta 1, instead of that we will write delta. Actually, this delta is actually the phase difference, which we will recognize later on. So let us see. We have to multiply this equation 2 by this factor n1 to the power half times e to the power minus I theta 1. So see, the first term in the RHS of this in the LHS of this equation 2, the first term is 1 by 2 n1 to the power minus half times e to the power I theta 1 times del n1 by del t. And you have to multiply this by n1 to the power plus half times e to the power minus I theta 1. So this factor will cancel out, and the remaining factor will be 1 over 2 times del n1 by del t. So you can see the first term is 1 over 2 del n1 by del t. Okay. Now we will actually multiply this second term by the same factor. But before that, you have to put the value of psi 1, which you have assumed here. Okay. So the second term is I times psi 1, and psi 1 will be written as n1 to the power half times e to the power I theta 1 and times del theta 1 by del t. So you can see I have written that this is I n1 to the power half e to the power I theta 1 del theta 1 by del t. Okay. And then we will multiply it by this factor n1 to the power half e to the power minus theta 1. Okay. And you can see this n1 to the power half and n1 to the power half, this will become n1. Okay. And e to the power I theta 1 times e to the power minus I theta 1, this product will be 1 because that will be e to the power 0. So this second term is I times n1 del theta 1 by del t. Now see the term in RHS. In RHS there is IT times psi 2. Now put the value of psi 2, which is equal to this much, n2 to the power half e to the power I theta 2. So this is minus IT n2 to the power half e to the power I theta 2. Okay. And then multiply by this factor. This is n1 to the power half times e to the power minus I theta 1. Now see, this will be minus IT and n1 times n2 whole to the power half. And there will be e to the power I theta 2 minus theta 1, and theta 2 minus theta 1 will be written as delta. Okay, and this can be written as minus it times n1 n2 to the power half, and instead of e to the power I delta, you can write cos delta plus I sin delta. Okay, now in the similar manner we will multiply this equation 3 by the factor n2 to the power half times e to the power minus I theta. See here. And when you will multiply by this factor to that equation in the just like equation 4 by analogy, you can write what will be the expression. Here also only there will be an exchange of the subscript 1 and 2. So when you will replace the subscript 1 by 2 and 2 by 1 in this equation 4, you will get the result. So you can see just by comparison. Here there is half del n1 by del 2. Here there will be half del n2 by del t. Okay. Here is I n1 del theta 1 by del t. So here will be I n2 del theta 2 by del t. Okay. And in RHS, there will be minus it, and this will remain same because n1 will become n2 and n2 will become n1. Okay, to the power half. And e to the power theta 2 will be replaced by theta 1 and theta 1 by theta 2. So there will be theta 1 minus theta 2. So that will be minus theta 2 minus theta 1. So e will to the power minus I delta will be here. Now e to the power minus I delta, this is equal to cos delta minus I sin delta, you know. Now see equation 4 and 5. You know, when two complexes are equal, then the real part of the first complex is equal to the real part of the second complex. The imaginary part of the first complex is equal to the imaginary part of the second complex. Okay. So we will now just compare or equate the real and imaginary parts of equation 4 and 5. So first of all, let us see, let us equate the real part of equation 4 and 5. You can see this half del n1 by del t, this is the real part of LHS. And what is the real part of RHS? You can see when you will multiply by this factor minus it times n1 n2 to the power half to the term I sin delta. I times I will be I square, which is minus 1, and here already minus is present, so that will become plus. So the real part of the complex in RHS is what? This will be t times n1 n2 to the power half times sin delta. Okay, so half del n1 by del t will be equal to t times n1 n2 to the power half times sin delta, and therefore del n1 by del t, that will be 2t times n1 n2 to the power half times sin delta. Okay, I think you are getting the things because this is a very simple calculation. Now similarly, the real part of the LHS of equation 5 is half del n2 by del t, and the real part of the RHS will be equal to this product of this minus it times n1 n2 half times minus I sin delta. Okay, so in the similar manner you can see there will be del n2 by del t equal to minus 2t times n1 n2 to the power half times sin delta. These two results for del n1 by del t and del n2 by del t we have obtained by equating the real parts of equation 4 and 5. Now we will equate the imaginary parts of the LHS and RHS of these two equations. Okay, you can see the imaginary part of the term in LHS is n1 times del theta 1 by del t, and in RHS the imaginary part is t times minus t times n1 n2 to the power half times cos delta. So what will be this del theta 1 by del t? You can see this will be minus t times n2 over n1 to the power half times cos delta. And similarly, when you will compare this imaginary part n2 times del theta 2 by del t with minus t times n1 n2 to the power half times cos delta, you will get this. This del theta 2 by del t is equal to minus t n1 over n2 to the power half cos delta. Okay. Now we have considered that n1 is the concentration of Cooper pair in left side and n2 is the concentration of Cooper pair in right side. But as we have assumed in the beginning, we have assumed that for simplicity our two superconductors are identical. So if two superconductors are identical, definitely we can take n1 almost equal to n2. Okay. So when n1 will be almost equal to n2, then from this equation 7, let us see what will be our result. This n2 over n1 will cancel in RHS. Here n1 by n2 will also cancel in RHS. Okay. So in that condition, del theta 1 by del t, what will be this? This will be minus t times cos delta. Okay. And del theta 2 by del t under this condition will be what? This is again minus t cos delta. Okay. So you can see in this condition del theta 1 by del t and del theta 2 by del t both are equal to t cos delta when n1 is equal to n2, so both will be equal. And therefore you can write that this del t theta 2 minus theta 1 is equal to 0. Okay. Clear? Now under the condition n1 is equal to n2, you can see here del n1 by del t and del n2 by del t. See the expression for these two in this equation 6. The RHS of both of these equations are equal, only there is a difference of sign. Okay. So when you will write this del n2 by del t as minus del n2 by del t, then RHS will be same. So from this equation 6, it is obvious that this del n2 by del t is just equal and opposite to this del n1 by del t. This is only this minus sign actually represents will represent actually the direction of current constituted by the Cooper pair. As you know, whenever a charge carrier flows, the rate of flow of charge carrier determines the electric current. So actually this del n2 by del t, this is the rate of change of concentration of charge carrier, and this will constitute current, and the value of the current will be proportional to this. When the rate of flow of charge carrier is larger, current is larger. So you know that current flow through a junction from 1 to 2 is proportional to del n2 by del t or minus del n1 by del t. That will be proportional. This is a very simple concept. Okay. And therefore we conclude from this equation 6, see here, that the supercurrent J of superconductor pairs across the junction depends on the phase difference delta This del N1 by del T and del N2 by del T determines the supercurrent, but that supercurrent depends on delta because sine delta is present here. Okay, so, and value will be same. It means the value of current in a left side and in right side, both in both sides will be same. So in the beginning I have told you that according to DC Josephson effect, there is a flow of DC current from one region to another without any loss of energy because current remains same. Okay, but that current depends on the phase difference delta. Okay, depends on phase difference delta. So from that result you can see if J is the current density. Actually J is current density, but commonly in higher physics we call it current, but this is in actual sense current density. Okay, and this J can be written as J naught sine delta. Actually here this J naught will be equal to what? That is equal to 2t times n1 n2 to the power half. 2t times n1 n2 to the power half. This is actually J naught. 2t times n1 n2 to the, sorry, this is not sorry, this will be not equal because this is proportional. Actually you know J is proportional to del n by del T, not equal. So there will be some proportionality constant too. Okay, but you can see this J naught is actually the maximum value of J. Okay, in fact the value of this J will depend on this T, you can see, and so J naught is proportional to T. Okay, and the current J naught is the maximum zero voltage current. When you do not apply any voltage, then current flows, but that current is not constant. That current does not vary with time, but that vary in accordance with this phase difference. So its frequency is zero, so this is a direct current. Okay, but J will vary in accordance with delta, and J naught is its maximum value. But you know sine delta has a maximum value of +1 and minimum value of -1. So this J will vary between plus J naught and minus J naught. Okay, so with no applied voltage a DC current will flow across the junction with a value between plus J naught and minus J naught. Okay, depending on the value of the phase difference delta equal to theta 2 minus theta 1. So in accordance with the phase difference theta, this J varies, but not in it does not vary with time in a sinusoidal manner. Okay, if instead of this sine delta here there will be sine omega t, then this will be AC. But this is a direct current because J is independent of time, its frequency is 0, and it flows when no voltage has been applied. So you can see in this way we find by this proper theory that a direct current will flow from one superconducting region to another through the insulating layer, thin insulating layer, when no voltage is applied across the junction. So without applying voltage we have direct current, and this is in fact the DC Josephson effect. Okay, I think the idea of or the concept of this DC Josephson effect is now very clear to you. Okay, so in the same manner, in the next lecture we will learn about the theory of AC Josephson effect. What is this AC Josephson effect and how that can be explained, we will learn in our next lecture. Okay, thank you very much.